This is the second video on counting partitions, and in this video we're counting partitions without worrying about how many parts the partitions have. So we're going to use the notation P sub n to represent the number of partitions of an n-element set where we don't care about the number of parts that we use. We can revisit one of the examples that we used for the previous video by looking at all the partitions of a three-element set. So with a three-element set, we have some of the partitions have one part, some of the partitions have three parts, and some of the partitions have two parts. This is a complete list of all the partitions that you can make from a three-element set. And so we would say that P sub 3 equals 5. The smaller cases are easy, like P sub 2 equals 2. There's only two ways to partition a two-element set. I invite you to see if you can see what they are. Even dumber is a one-element set. The only way to partition a one-element set is by just making that one element be in a part by itself. And the sort of a weird case that's important for this video is this very technical case that P of 0 is 1, and that's because, really just because of the technical definition here, the empty set is a partition of the empty set. If you look at the definition of a partition, then this really is true. It seems like a dumb thing to say, but for this particular video, we'll see why we need to include that. So now, to look at the recursive model, let's look at the example where we're trying to count all the partitions of a four-element set, 1, 2, 3, 4, given that we already know how to count the number of partitions of smaller sets. And so I'll be referring to the smaller partitions, and the only one that was interesting is this one. This one had 5 possibilities, so I'm going to include that there. So now let's think about what would happen if we, how we might want to go about creating a partition of a four-element set. I'm going to suggest that we do this in 2 steps. We first decide what part of the partition is going to include the number 4. The reason I'm using the number 4 is because it's the number that it's the new number that wasn't available in the thing that I circled in green. The stuff in the green box are all partitions of 1, 2, 3, and so for those partitions, 4 was not even an option. So I'm going to think about my new partition by thinking about where the new number goes, where the 4 goes. So one way we can do that is just to decide what the part that has 4 in it looks like. That part could be 4 by itself, or it could be 4 with any of the numbers 1, 2, 3, 4. So step 1 is going to be choosing a subset of 1, 2, 3, even the empty set, and adding the element 4 to it. So this is, I keep doing that. We're going to take any subset of 1, 2, 3, possibly empty, and we're going to add the number 4 to it. So for example, if I picked the set 1, 2 in this step, then the partition part that I will have made is the set 1 set 1, 2, 4. So whatever I pick, I'm going to add a 4 to it, and we'll look at an example here in a second. After I've done that, all that does is, I'll just give this as an example. So if 1, 2 is picked, then this is referring to making this part. So I'm going to take any subset of 1, 2, 3, and then add the 4 to it. So that's going to be one part of my partition. The rest of the partition has to be made by partitioning up whatever numbers I didn't use. So in this case, the only number I didn't use was the number 3, and so I would be building a partition of the set with just 3 in it. And there's only one option for that. This would be a partition of the remaining elements. So I have this part 1, 2, 1, 2, 4, and I have this partition, just the singleton set 3, and I'm going to stick this guy right in there. So I will have created a partition, namely the one that has this 3 by itself and the 1, 2, 4 together. That's a valid partition of the set 1, 2, 3, 4. So I'm going to do those 2 steps in all possible ways. Choosing, first of all, building the part of my partition that uses the 4, and then just picking another partition of the remaining elements and combining the 2. The problem with this as an algorithm is that the number of choices that I have in step 2 depends on how many things I chose in step 1. So I'm not going to be able to tell you how many choices you have for step 2 all the time because it depends on how many things you chose in step one. And so this gives us the key idea for this combinatorial proof, which is we need to break this into cases based on how many things I choose in step one. So I'm always going to follow these two steps, but I'm going to break it into cases based on how many things I choose in step one. So here's an illustration of what this will look like to build all of the partitions of 1, 2, 3, 4. And you'll notice that I am breaking these into cases based on how many things I'm choosing in step one. So the first thing I could do is choose nothing in step one. When I choose the subset here, the empty set, and add 4 to it, that means I'm starting off with a 0 element set in step one, and then I add the 4 to it, which gives me that part. Here I didn't list all the partitions I could have in step two because there were 5 of them and it took up too much space, but they're the 5 that I just listed on the previous slide. And so I would add the singleton set 4 to any partition of 1, 2, 3, and that's going to give me partitions of 1, 2, 3, 4. And in all of those partitions of 1, 2, 3, 4, the 4 will be by itself. The second case would be where I'm choosing 1 element sets in step one. If I pick a 1 element set, then adding a 4 to it gives me a 2 element part with a 4 in it, which means I have to partition the other two elements, and in each case there are 2 ways to do that. So in this case, using 1, 4 as my part that uses the 4 leaves me with the numbers 2 and 3, and there's 2 different ways to partition 2 and 3. And so in this case, I did go ahead and combine these. So this is what happens when I combine my new part 1, 4 with either of these partitions of 2, 3. And then I just do it again. So if I use 2, 4, that means I have 1 and 3 left. These are the 2 ways to partition 1 and 3, and that leads to these 2 possible partitions of 1, 2, 3, 4. And so the relevant number here is how many ways there were to pick a 1 element set, and then the fact that there's 2 options here. The 2 options here is because of P2. P2 is the number of ways to partition a 2 element set. The third case would be where I'm picking 2 element sets initially in step one. So if I pick 2 element sets from step one, that gives me the part of the partition that has the 4 in it. We have 3 things there, 1, 2, 4, 1, 3, 4, or 2, 3, 4. And then all that's left to do is, from each of those, I'm going to partition just 1 thing in each case. So if you're using 1, 2, 4 as 1 part, then you're partitioning 3. If you're using 1, 3, 4 as 1 part, then you're partitioning 2. And if you pick 2, 3, 4 as 1 part, then you're just partitioning 1. So in each case, you're only partitioning 1 thing. We know there's only 1 way to do that. And then again, this is what the result would be for combining this part with this partition, this part with this partition, this part with this partition. Each one's going to lead to this new thing. And then finally, if I picked all 3 things available in step one, then that's going to mean that my the part of my partition with a 4 is going to be the whole thing, which means that there's nothing really to combine it with. That's the empty set partition, and that gives me just the partition with just that one part. So over here, there are 5 that look like this first case, which I didn't list them all because there were 5. So that's because P3 is 5. So in each case, the 2 things that are going into the number that I'm seeing are how many subsets I could have started with, and then for each of those, how big the partition is for the second part. And so this is where I'm going to get my identity. So the number of ways that I can get a 0 element set is 3 choose 0. The number of ways I can get a 1 element set is 3 choose 1. The number of ways I can get a 2 element set is 3 choose 2. And the number of ways I can get a 3-element set is 3 choose 3. So that's how many rows I have in this thing. And then for each one of them, the number of ways to do step 2, the number of options here, that's just a partition of 1, 2, 3. That's p sub 3. I know p sub 3 is 5, but we're going to refer to it with this notation. So here there's 2 options for each of these because p sub 2 is 2. There's only 1 option for each of these because p sub 1 is 1. And of course there's this really strange one to think about, but it's there because p sub 0 is 1. So what I have is the number of partitions in each of these blocks is just the product of how many choices I have for the set in step 1 and how many choices I have for the partition in step 2. And so this is the first case, 3 choose 0 times p3. Second case, 3 choose 1 times p2. Third case, and the fourth case. So when I add all those together, I get my total. There are 15 different ways to partition a 4-element set. If I write this up using the general n instead of just 4, you'll see all the components, but this is what it looks like. Here I'm going to think about my new problem as partitioning 1 through n plus 1, and I don't always make that choice when I go from one step to the next, but in this case it makes it a lot easier to say what all the values are. So I'm thinking about what happens when n plus 1, the element n plus 1 becomes available for the first time as part of the partition problem. So that means what I'm counting here is p sub n plus 1, the number of ways to partition an n plus 1 element steps. We define the 2 steps that we're going to do to build these things, just like we did before, except we say ahead of time that we're going to break these into cases based on how many things we're choosing in step 1. So case K, what I'm going to refer to as case K, is going to be where I start in step 1 by choosing any k element subset of 1 through n. So I know exactly how many elements I'm picking, and then I add the n plus 1 to it. So the same way I picked subset of 1 through 3 and added the 4 to it, that's exactly what I'm doing here. But we know the number of ways to pick a k-element subset of 1 through n is n choose k. So there are n choose k ways to do step 1. Once you do that, you're going to have n minus k elements remaining. You will have taken k elements of 1 through n away, and you will have the other n minus k elements of that set left that still need to be partitioned. And you can partition those into any number of parts that you want. And so the number of ways to partition n minus k elements into any number of parts, that's what this represents. P n minus k means the number of ways to partition an n minus k element set. So in terms of the notation we have here, there are n choose k ways to do step 1 and p sub n minus k ways to do step 2. So if I multiply those 2 things together, that's the number of ways that I can form a partition in case K. K is the number of choices that I have for this set, and so that means that the K can be as small as 0, because you can pick a 0-element subset to start with, or K can be as large as n. You can pick an n-element subset to start with. So you would have a case like this for any value of k between 0 and n, and so that's why in the end our answer is going to be the sum for all those possible values of k, so k going from 0 to n, and the answer for that case is n choose k times p sub n minus k. So the recurrent says that that should be equal, this expression should be equal to p sub n plus 1. And that's the recurrence relation.